Swayam Prabha. Digital India. Educated India.
Yeah. So, okay, I'll start. So, my name is Nikhil Sharma. I am a PhD student in the Department of Chemical Engineering, IIT Bombay. So, I'm going to present a paper on variable structure modeling and simulation for the cold startup of distillation columns. Along with me, the co-authors for this paper are Rahul Paknikar, who is an MTech student in the Department of Computer Science and Engineering, IIT Bombay, Professor Kanan Modgali, IIT Bombay, and Dr. Sunil Shah, Modelicon Infotech LLP. So, moving on to introduction. So operation of conventional batch distillation can be categorized into three parts, that is startup period, production period, and shutdown period. Generally, production period is most time consuming, but in case of complex operations such as high purity or azeotropic separations, the startup time may also be considerable. The startup and shutdown models are inherently transient and discontinuous in nature. Therefore, the design and control around the steady state are not valid for these startup and shutdown operations. So moving on to the scope of startup operations, the dynamic simulation of startup and shutdown operations is beneficial in modeling, design, control, and operability of distillation columns. Training of operators can be done for designers. The information may help in avoiding operability and control problems. Modeling of startup operations is also interest for optimizing a distillation system, wherein for optimization to initialize certain assumptions are involved, that is pseudo-warm, steady state, initial total reflux, etc. That can be avoided if in the presence of a proper startup model. Yeah. So objective, despite being critical operations, there is limited literature available for startup and shutdown operations. This is mainly due to inherent complexity involved in modeling the design, dynamic behavior such as phase change, variable structure, and model switching during the simulation. Some publications are available which takes into account many assumptions like ignoring transition or adding trivial equations, but most of the time these are not valid assumptions. So in our work, a unique blending of rigorous modeling of the dynamic behavior of startup operations of distillation systems with system level discretization is done. System level discretization is achieved through a schedule that is consisting of system component based tasks and events. So here I'll show general startup sequence for a batch distillation. So in the step one, we have considered that feed is charged to the reboiler and energy, that is heat energy is supplied. So this supplied energy should result in increasing the temperature. So only these equations will prevail in this model, and the other components of the distillation column, such as the trays and the condenser, are inactive during this step of the simulation. When as soon as the bubble point is reached, as we are providing, so vapor will start coming out of the reboiler and will go to the tray just above it. So as soon as the bubble point is reached, the VLE equation should be incorporated in the reboiler. So this is the switching of the model. So in the step two, the reboiler equations will have VLE model, as well as the vapor is going to the tray just above. So there is an addition of the simulation in the tray, and when trays get the vapors are getting accumulated there, and with the energy of the vapor, it is going to get heated also. When the bubble point in the tray is reached, so the vapor will start going out of the tray and it will accumulate in the second tray. Likewise, the entire trays will be filled, and when the bubble point of the top tray is reached, the vapors will go to the condenser. In this step, the third component is condenser should be added in the simulation. And when the holdup of the condenser is reached, the liquid will flow back to the top tray, and at this mode, it is run at the total reflux mode for some time. And after certain time, we can discharge the product out. So this is the general startup sequence. So we can see to model this behavior, we have to phenomena of changing the equations of the model in between the simulation. That is, VLE equations has to incorporated addition or removal of the components is required. So this makes the modeling and simulation complex for startups processes. So in order to do this, we have developed a scheduling framework in Open Modelica. Open Modelica is a general purpose modeling and simulation environment, Modelica does not provide support for scheduling. So Modelica modeling of discrete behavior is achieved through a schedule consisting of system component based tasks and event. The schedule is a connected graph and is compliant with control flow work patterns. It simulates only the active components of the system by auto discretizing the model. Yeah. And to also enable the variable structure modeling that we have seen, that we have to incorporate the wheel equations after some time. So we have leveraged the scheduling framework. Yeah. So it also provides a Modelica package in form of scheduler library to construct a module. So here is the general framework. A model developer has to furnish the system level model and the schedule. Schedule means at what event we have to add or remove the components. The scheduling engine, which is written in Python language, it interacts with the Open Modelica compiler through 0MQ interface, and it simulates the task and monitors the events. If the conditions is satisfied, then it triggers the event. Otherwise, it looks for the end of the time or the end of the simulation, and the loop continues. So, in order to test this, there is an example. So, we have considered methanol acetone mixture for a batch distillation system, and the startup is studied. So, mixture of methanol and acetone is fed to reboiler. The column is operated at total reflux. So, column specification are there are 15 number of stages. Tray and condenser hold up are 2 gram moles each. It is operated at atmospheric pressure, and the charge is 70 gram moles in the ratio of the composition is 0.64 and 0.36, 0.64 and 0.36 mole fractions for methanol and acetone respectively. The physical properties are evaluated using an RTL model and density through Racket density relations. So this is the experimental setup we have. So this is the reboiler, and the column has 3 sections of 6, and 3 trays, so that it comprises of 15 trays and a condenser. So we have intermediate temperature sensors to calculate the temperature. So here I would like to show the video how the startup is done. Yeah. So 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 you can see that feed is charged in the reboiler and it is getting heated. So initially the trays are empty. So one by one, that vapor is reaching to the trays and getting accumulated. You can see the top trays are empty now, and after some time it starts getting filled. So this is now the top trays are also filled one by one, and we can say that the total reflux to start. So this is the modeling we have followed for the our simulation. So I'll stop this video here and go back to the presentation. Yeah. So these are the comparison of the experiment and simulation results for VLE in intermediate rate. So we have the temperature sensors at tray number 6, 12, and 15. So at experimentally, it takes 233 seconds to reach the bubble point. And at 12 number tray number 12, it takes 490 seconds, and at tray 15, it takes 582 seconds. And the simulation results are also comparable. So I would like to show how we perform the simulation here. Yeah, basically to show you the interface of the scheduler. So this is the Open Modelica interface. This is the scheduler. We have task and event based components, and various dependencies to event to take place. And this is the object oriented model for the batch distillation system. So we have thermodynamic functions, enthalpies, and the object oriented model for condenser, reboiler, and trays. So this is what we want to achieve. Like this is where my cursor is. The feed is charged to the reboiler at first. Only these components are solved. When the reboiler is filled, that is up to 70 gram moles, heat energy is provided at the step 2. When the bubble point is reached, there is an addition of the just a tray just above the reboiler, and there is an addition of the VL equations also. So the model of the reboiler is switched, and similar, and when the bubble point is reached, it is replaced with the VLE trace, and the tray just above is replaced with is added with just a normal energy balance equation, that is Q is equal to mcp delta t. So in this way the entire model is uh, made. And for scheduling, so in the first step we have to charge the feed and the reboiler only. And with the event, as soon as the 70 gram moles of the feed is charged to the reboiler, this step should be finished, and the reboiler should be replaced with the bubble reboiler, which contains the VL equations. And when the bubble point is reached in the reboiler, uh, there is an addition of the tray, you can see here. So this is where this shelling framework works. And moving on to the results, so I'd like to first show. So this is the simulation of the first step. It includes only the feed and the reboiler. So we want to see. So as soon as it is finished, that is 70 gram moles of feed is charged in the reboiler, this step is completed, right? And in the next step, only heat energy is provided. So the hold up remains the constant. Hold up remains constant. And we'll see here the temperatures profile of the reboiler. So this is the temperature profile, and this is the bubble point. As soon as the bubble point is reached, this simulation is stops. So I'll plot all the holdups one by one. So one, two, three. Yeah. So you can see initially it is filled with 70 gram moles, and the heat energy is provided. So here the holdup remains constant, and as soon as the bubble point is reached, the vapor starts going out of the reboiler, and the holdup decreases. So in this way, the entire simulation can be performed. We can see the temperature profiles for every component. So moving on to the slides again. So our simulation results are in comparison. So next we have taken the startup of a continuous distillation column. So an equimolar mixture of benzene and toluene is fed to the reboiler. The column is operated again at total reflux. Then a continuous feed stream is introduced, and products are withdrawn. So here we have taken three number of stages, and tray holdup is 12.5 gram moles, and condenser 100 gram mole. It is operated at atmospheric pressure with a charge of 1000 gram moles with an equimolar feed. So here we have taken the ideal system, that is K values are calculated using Raoult's law, enthalpy and density with the ideal gas or vapor and relations, and Reckitt density relations respectively. So these are the simulation results. So I am just plot. So as explained previously, the components are added one by one on the application of on the trigger of the bubble point, and I am just plotting the composition profile in the condenser, that is the distillate. So at the steady state, we can see around 0.88 and 0.112 mole fractions of both the components respectively. And for the validation purpose, we have used the DWSIM, which is an open source alternate to Aspen Plus. So our simulation results, steady state results, are exactly matching here with the DWSIM. So it validates our model as well as the simulation results for the continuous operations. So having proposed this model and validated this, uh, we can use it to see which startup policy is better. For example, here we have charged feed to the condenser. Then another application can be the feed is charged to the reboiler with heavy components, and the light components are feed with the in the condenser, and then the column is filled with the feed. So this is the another type of startup policy. So we can with the brute force method we can see which startup policy is best. So moving on to the conclusion, despite being a crucial operation for both batch and continuous operation, there is a limited literature available for startup operations. Startup models will be helpful in the accurate optimization of the process. Startup models are also vital for operator training and design. A generic framework for the startup of a process plant is developed by blending a rigorous training model with system level discretization. And future work includes optimizing these operations using variable structure optimization, implementing a control strategy, and extending the scheduling framework for the startup and shutdown of the process plants. Thank you.
Hello. In the continuous distillation column 1, the experimental study you use for the 3 stages, but DWCM validation use of 5 stages. Have you number of stages for that continuous distillation column used at the 3 stages, but in the validation step with the DWCM you consider the 5 stages.
Okay. Okay. So I'll repeat the question. Is the question is in the continuous stage for the validation, I have a different number of trays. Is it the question? Yes. Okay. So for the batch distillation, I had taken 15 trays, and it was 15 trays were available with the setup that I have. And for the continuous, so it was validated with the experimental results. So since the experimental results are validated, I moved on to the continuous distillation. And for the continuous, I have simulated the same unit with the DWSIM. So DWSIM is a steady state solver. So it gives us the steady state results. And so I have operated the startup with the my scheduler that we have developed in the lab, and the in order to check the results of the continuous distillation, I have just checked the steady state results, because we cannot check through the other simulators the startup operation. So in order to check the steady state results, a different question with a different number of trays has been taken. So it is solved with DWSIM in order to validate.
Got it, got it.
Have I answered your question?
Yeah. Any other questions? Okay. If not, we'll thank the speaker once again, and we'll have the